I said keep quiet, just have an open mind. Very simple. Just a simple diagram. Open mind, open mind, open mind. Okay, so we are doing two courses: computer architecture and microprocessors. So and then when we started, I taught you how to use logic gates to design relational logic, right? Taught you how to use relational logic to design differential logic with memory, right? And then I taught you how to design FSMs, finite state machines. They are all in the slides every day. Nothing is coming from outside. They are all in the slides. So I told you what. So for the computer architecture, you're going to be designing the schematics, right? So I would say, for instance, these are all components of micro of the computer. We have another here. We just did another design right now, right? So and I'll give you a truth table, as we did a truth table. Now design a half adder out of that truth table, right? Design a full adder out of that truth table. But here you are doing the schematics of that truth table, right? Then after that, you are maybe you'll be doing 16-bit adder or not 4-bit, I don't know. 16-bit. Okay, I School of so 16-bit adder or 4-bit adder, whatever it is. Very easy, right? So you design that, and then that will be the schematic. That will be for computer architecture for question one. For microprocessors, question one, how is happening that I'm going to give you the answer for what it really. So in an hour's time, after you finish computer architecture, you know whether you are right or wrong in an hour's time because all the answers you're going to put the answers. Keep quiet. The first one is, let's say, keep quiet. The first one is an adder. The schematic for an adder. You have done that. You have done that already. You want to do that for the maybe in an hour's time. It will be use very long code and adder. You're coding an adder. So means that I'll give you the schematic for the adder that I said draw within that exam. So you know whether you were right or wrong. So you just mark yourself mentally, right? And then so here you write the code. Have adder model have adder input output simple connect your because when I'll give you let's say the half adder, right? Input output I'll give you this. Just write a very long code for this. You know your input output. You know the date. Just connect this. Just write the code and finish. That would be question one. Now question two. I showed you how to design a register file from the scratch. Right? I showed you the design of a register file. Something that looks like this. Listen carefully. Single input or one input, single input, dual. In case you rest more, you know what I'm doing. Dual output 32 by 32 register file. Right now, I mean that this one has an input D or whatever is here. I don't know what is the number of bits for D. Go and solve it on your own because it's coming. So I'll give you a register. I'm not saying it's 32 by 32. That is an example. So there will be D and I'll ask you what will be what is the data weight for D here, right? Now this is dual port, so it has two outputs, QA and what? QB. What is the data weight for here and here?
Simple.
It has the right enable. W. What is the data weight for the right enable? It has RA, read address A. read address A. What is the data weight? It has read address B. What is the data weight, right? Simple as that. So once you get all this, then I will say draw the internal architecture of the 32 by 32 register power and it's in your slides. So what is that about this? Easy, right? Now that will be for computer architecture. You come to microprocessors, I'll give you the internal architecture. That means that you already know whether you have the right one or right. Then I'll ask you to use very low code to design the internal architecture for the register power. Right now, we didn't teach, I didn't show you how to design memory in Verilog, but briefly, in case you are giving input and output, right? You are giving for the file against generated, you are giving input and output. So something like model register file, right? We have the inputs like what? How was the input? I had the input, right? I had the read address. I had read address A, read address what? Then what? So right, and then I had outputs were QA, QB. So you just come and declare inputs. Some number of bits is the array will be array will be different. This one will be there. Whenever it will be the same. Then output QB and all of that. Right? Now we have to declare, we have to design memory, and then anytime I'm drawing memory, I do something like this. Right? I always do something like this. Right? And I say we have the width of the memory, and then we have how many locations there is. Right? So once you're designing memory, it just register the width. Listen carefully, the width. Right? So the width will be whatever, maybe 31 is to 0. It means that 31 bits each. Here will be 31 bits, 31 bits, 31 bits, right? And then I name it, any register one, maybe red, one, whatever. And then probably 64 is to 63 is to 0. So this just means that this one has a width of 32, and then the number of locations is what? 64. As easy as that, right? So once you declare this, you must read from the memory. Right? So how do we write code to read from the memory? Right? So it means that we are reading, and then we are reading to the QA and QB, because the QA and QB are our output. I must give it the address. So QA, depending on, in case I use QA as a register file, I must use always as something then inside. But if I just declare it as a wire, I must use what? Assign. You guys know all this already. So assign QA is equals to, so I call the memory reg1. Then I give it RA. So I give it an address, RA, and then it will just read from this memory and assign it to this. Easy as that. Then QB, assign QB is equals to reg1 RB. Right? So it means that here I'll be able to at the same time read two locations at the same time and assign it to an output. Is that clear? It's as easy as that, right? So now how do I write to the memory? Now the memory actually this is register power. So for the memory, I think we have write enable, very important, write enable, and then we have D, right? So to write to the memory, we have to come. So I'm cleaning all this. So this part is just for reading. The part I guess this was for reading. So now writing to the memory. I'm using W. So and then I have to write. I declared it as what? What? 31 is to 0. 1, 63 is to 0, right? Right. So it means that I have reg 1s here. The reg 1s are here. Right. So how do I write this? So I have to call one of I think the right address is RW, right address. It has a number of bits, right? So I have to call. So I'm writing, right? But I need to give it an address. I need to give it data, right? So what do I do? Always, we have done this already. Always at or maybe or. If write a label, if right, if write a label, register one, right? Register one. Give it an address. RW, right? Is equal to what? D. I'm done. So I've been able to write it there. It's as simple as that. Right? Next. So you need to be like question 2. So after we draw the schematic for the architecture, you come and draw you come and give the variable code for the microprocessor. Right? So that will be like question 2. Or something. Question 3. Question 3. Question 3 is memory. Memory, right? Memory pop-up. How does memory look like? It looks like we have an address. Keep quiet. We have an address. Or I should stop. Keep quiet. Keep quiet. For memory, right? Whatever the size. Wait. 32 by 8 mega by 82 SRAM. We have done this already. I thought this roots so it means that now I'm going to punish you for not listening. So your address. So now from here, I'll just say what is the number of bits for the address. Simple. Then for the memory, we have dual ports. So data, right? So I'll just say, look, what is the address here? Finish, right? Then I'll just say, oh, okay, we have this is 8 megabyte. Take to register 8 memory, right? So if I have a 4K by 8-bit memory, combine this one to make this. How many of this makes it show working? How you had it? As simple as that, right? Simple. Then this will be for computer etc. You come to microprocessor, you design the variable code for the memory here. Simple. I'm not going to show that. I always know how to do the register power. Almost the same process, follow the same process. The last question will be probably so the last one will be okay, I've seen okay. So many, I can't count. Okay. Question 4. And design an ALU. I gave it to you as homework. Everybody had it wrong. So go and sit down and design the schematics for an ALU. Then for the microprocessor, it will be design somebody's video in power. I am videoing already. I'll make it available to you guys. So ALU design, right? That will be for the schematic for computer architecture. The microprocessor use Verilog to design your ALU. So your ALU looks like this. Simple. ALU, you have an output, you have input A, B, out. You have function, some select function here. Then I will say U A or B, A, X or B, whatever, right? An easy way. Draw the schematic, then come to the variable code. You have ALU has A, B inputs out to the function. Just write the code for it in Verilog. As easy as that. That's it. So, and then that was the question 4. Then the last question will be and FSM. Both. You are doing both. So you draw schematic for this one. You come and write code for this one. You see how easy that is. You draw schematic, computer architecture, you are doing all the schematics. Microprocessors, you are writing the code. You see how easy. You see how easy I made it for you guys. So the last one will be an FSM. Right? What am I giving you? I'm giving you an FSM. I'll give you a statement, right? Then you draw the state diagram. Those ones. State A, state B, X, you have inputs of input A or whatever. You have output 0 or 1, whatever. Reset, that kind of stuff, right? Draw the schematic, then you draw the next state table. I showed you how to do it already, so there's no issue. So you draw the next state table for this state diagram. Then you draw the output. The output table. You fill out the output table. Then using your output and then the state table or something like that. You derive some Boolean equations for your states and then your outputs. I showed you how to do it. It's in your slides. I've done this video for you. You can go and watch it and see how it's done. Then after that, the last one is that you're going to draw the schematic of what you have done. The schematic. You already know that for FSM, you have what is here? You have an input, right? And then we have what is it? Anybody? All of you wrong for net state logic, right? Is here. Then the next state logic feeds into your state register, right? And then the different feeds into your output logic, right? And then this one goes to your output. And then from here, this comes and feeds back here. Right? Now it depends. I can, as I said, I can say use. There are two types of FSMs. I say merely machine or more machine. So if it this one, more machine. If it is merely the input here will be combined here. Right? The input here will go to the output logic. So it means that now after you have done your state value and everything, you draw the circuit. So you are going to follow procedure like this. You have the next state logic. Using the next state table, you derive your Boolean equations. You just come and draw your next state logic. Some aggregate, whatever. You put your state register here. Then you draw your output logic. You draw your output logic. You draw your output logic, and then you are done. For computer architecture. For microprocessors, you are going to design the very low code for this one. Of what you have designed already. Right? So I'll give you the diagram. Then you write the code. 1 hour for 2 hours. So as easy as that. So here, for the FSM, I think for the slide I showed you how to design the code for the FSM, right? So I don't have to repeat it here. So you go and study it, watch the video, and then you can tell me about it. Yeah, write it down. If you like 30 minutes. Alright, so thank you very much. Okay, and so once I check your design, you can go. So thank you then. Good luck in the exam. If you score 0 as well, that's how it can be. Hey, move. The questions are here. Go here. Yeah, put it here. Go here. The questions are here. What's that? Tomorrow we'll see you. Tomorrow.